Let's turn the tape on. So we're started. So we have a homework due tonight on the that one on the coordinate plane, right? Which has various things in it, including circles. And then coming up on Wednesday is this homework on ellipse, which is not as long as this homework on the coordinate plane. Let me open this one since it's due tonight and at midnight, and this is like really your first real mathematical content homework that's due right tonight. So so let's look at this, and I want to ask you if you have any questions so we can look at some of the questions there, but I had a couple of them that people had questions about. So I would I'm going to mention those if I can find them. Oh yeah, these two for sure, huh? Yeah, number 6, right? Okay, yeah, I had questions on number 6, and then I had questions on this one, number 5, right? Okay, so now when I'm looking at these in class, right? This is gonna the numbers that I have, these are algorithmic, the problems are algorithmic. Okay, so numbers that I get from that I get in my version may differ from yours, but the nature of the solution, the form of the solution will be the same. So so the examples are good to see. So let's look at this one, because this is very similar to one of the problems that we did in class. Then we'll talk about this one. This one's just a little bit complicated because of the just all the words there, that the verbiage there, or terminology that's used in the problem. Sometimes they tell you you're going to use something, and it really may not be necessary to use it. So so when you're reading those instructions, don't think that I necessarily have to do what they're suggesting. But this one says use the distance formula, and indeed we are going to use the distance formula here, because the question says find a point on the y-axis. I think we had an example with the x-axis, but find a point on the y-axis that's equidistant. That means the same distance from these two given points. Okay, and so let's let me pull out some blank paper here and remind me of these 2 points: 8 and -8, and 2 and 2. Okay, so if we so I'm going to lower the screen here. If we scribble up, just a really rough picture of this, right? Okay, which one was this, number 5? If we scribble a really rough picture of this, it's going to be rough because just graphing here, right? Okay. You want to point on the you want to point here on the y-axis, right? That's again the same distance from 2 and 2, right? Which would be somewhere over here in the first quadrant. And then what was the other one? -8 and 8. +8 and -8. Oh, I see. So +8 and -8, maybe somewhere down here, right? But so 2 and 2, and then 8 and -8. But you want the point to be on the y-axis, right? Okay, so obviously the point that's one easy point that's the same distance between the 2 points, right, is the midpoint between the 2 points, but that's easy to calculate, right? But we don't want the midpoint, because that's obviously not going to be on the y-axis. We want a point on the y-axis that's the same distance from these 2 points. So just eyeballing it, maybe right there. Does that look? No, that's not it. Okay, that point is much closer to 2, I think, at least in this drawing, right, than 8 - 8, right? Okay, so I didn't even position the point very well, but of course I don't have these points graphed very accurately either. So, so nothing in this picture is probably very helpful, other than just the fact that we have a diagram there, right? So we want to point on the, but it's got to be on the y-axis, right? That's the same distance between those 2 points. Okay, so you don't know where that point is, right? So that point is going to have to be a variable, right? It's going to have to be an unknown. Okay, and that's really a key step in the problem here. You're going to have to give a variable name to this unknown point, right? But you do know that it's on the y-axis. So the coordinates of the point are not a complete mystery to you, right? Since it's on the y-axis, that means the x-coordinate is 0, right? So that point that coordinate you can fill in, but the y-coordinate you do not know. So you're going to have to leave that as an unknown, as a variable, right? So just give it a name, because you want to be able to work with that point in the problem, okay? So, you've got to have something written down for the point, but the y-coordinate we cannot specify exactly, right? That's the whole point of the problem, find the value of y-coordinate. So we'll give it an unknown y-coordinate there, right? I'm just calling it y since it's on the y-axis, but you can pick any unknown that you like, right? Any variable like will work there, okay? And now, here's where the distance formula comes in, right? Calculate the distance from this unknown point, right, to the 2 given points, correct? Right, so we just use our distance formula, and that we're pretty good at, right? So we know it's going to be the square root of what you take the difference in the x coordinates, right? So square that, and then plus the difference in the y coordinates, right? You really can take that difference in either order, since you're squaring both quantities. Signs are not going to be an issue here. So if you wanted to write that as y minus 2 instead of 2 minus y, okay, square that. And the square root of that, of course, is going to be this distance here, right? Okay. And then you also calculate the other distance, right? So that looks like what? 8 minus 0 squared, right? The difference in the x coordinate squared plus, and then minus 8 minus y squared, right? The difference in the y coordinate, square that, and that's this second distance. And we want those 2 distances to be the same. So we simply equate those 2 expressions, right? So there's your equation, right? You're going to have this square root equal to this square. I have the equation written vertically instead of horizontally, but still equation here, right? Okay. Those 2 expressions are equal, right? And now it's just a matter of solving that equation. So this is where your algebra skills come into play, right? But the real logic of the problem you've already done, okay? It's setting up those 2 distance expressions and then setting them equal to each other. Let's see, in this particular case, to solve this, right? Let's square both sides of the equation, and so we would get 2 squared, because 2 minus 0 is 2 squared, right? Plus 2 minus y squared is equal to, and then 8 squared, right? Plus the minus 8 minus y squared, right? So I'm just erasing the square roots, essentially. And now let's simplify both sides of the equation, okay? So that means we're going to carry out the arithmetic on both sides of the equation by hand, right? So 2 squared is 4. And then when you square 2 minus y squared, remember, that's where you don't want to make this silly mistake, right? When you square 2 minus y, that means you have to multiply it by itself. Let me go ahead and write that down. So you have 2 minus y times 2 minus y is equal to 8 squared is easy. That's 64. And then you're squaring the minus 8 minus y. So you're multiplying it by itself. This may be more steps than you need when you're doing this on paper at home, okay? Right? But that's fine. So we have 4 minus, and now let's, is it 4 minus? No, it's 4 plus, right? There, I left off my plus sign here, okay? So we have 4 plus, and then 2 minus y times 2 minus y. Well, remember, every term here by every term here, you take the 2 and the minus y and you multiply each of those terms by the 2 and the minus y in the second set of parentheses, right? So that's going to give you something like 2 times 2 is 4, and then you'll have a minus 2y, and then another minus 2y, and then minus y times minus y is plus y squared, right? And then here we get 64, and then let's see, minus 8 times minus 8 is 64 again, right? And then we will have what? Is it plus 8y? Plus 8y, you have to be careful with signs. Minus 8 times minus y is plus 8y, minus y times minus y is plus 8y again, and then minus y times minus y is y squared. And now we just continue simplifying. You know, you can still add things together here. 4 plus 4 is 8, minus 4y plus y squared equals, what is that, 128 plus 16y plus y squared. And now I see some nice things that will happen here, right? You can immediately see that the y squares on both sides of the equation are going to cancel. So you really don't have a y squared term in this equation. That's good. That makes it much easier to solve, right? So to solve this, we can just isolate the y's on one side of the equation, right? And the constants on the other side of the equation. So I'm going to take this minus 4y and move it to the right-hand side. So I have 16y plus 4y, and then let's take this 128 and move it to the left-hand side. So I have 8 minus 128. So it looks like 20y is equal to minus 120, which means y is equal to -6. Okay, so yeah, so I didn't have that drawn very well, but it is on that our mystery point is on the lower side of the y-axis, right? The y-coordinate there is -6 for this version of the problem. So your version of the problem might be slightly different, okay? But here are the steps. All right, let's look at let's look now at the second one. So this says use the distance formula and the midpoint formula. Let's see if we need them both. So it says find the lengths of the medians of a triangle that has vertices at those 3 given points. But now it's going to tell you what a median is. So it says a median is a line segment from a vertex of the triangle to the midpoint of the opposite side. That's obscured there, but that's what a median is, right? It's a line segment from the vertex of a triangle to the midpoint of the opposite side. Okay, so so again, let's make a picture here. Did y'all write those 3 points down for me? 1, 3, 4, 7, 8, 1. Let me see if I can scribble this. This is really going to be. So what were they? 1, 3, 1, 3, maybe here, and what? 4, 7 up there somewhere, and then 8, 1. 8, 1 back down here, over here. So, you know, there's roughly the shape of that triangle that's being described, right? And then what they're further telling us, right, is something about the, they're asking us about the medians. Is it the lengths of the medians? So again, the medians, there are 3 of them. And if you start at one vertex and go to the midpoint of the opposite side, that is that line segment. Okay. And so you can form 3 of those, right? One this way, and then the other one starting at this vertex and going up to this midpoint. Oh, you'll notice there that notice those medians, they all intersected at the same point, right there. And that's not a coincidence. Okay, medians of triangles will all intersect in the middle of the triangle in a single point. Okay. But that's not the point of this question, right? We just want to find what the lengths of these medians are. All right, so this is point A. Okay. And so point A had coordinates what? 3, 1, no, 1, 3, 1, 3. And so over here, I think they're calling this midpoint, the other end of that median, they're labeling that as A prime. Was that confusing? Okay. So when they say the median A prime, they're talking about median that emanates from vertex A over to the other side. Okay. So we want to find the length of that median. And so that means we need to know the coordinates of this point, right? So we can use the distance formula. But remember, the coordinates of this point, they're the midpoint between these two other vertices. So that's the midpoint between B and C. Okay. So according to our midpoint formula, what is then the coordinates for A prime? Well, you just average the coordinates for B and C, right? So what was the x coordinate of B? 4. And then for C, it was what, 8? And divide by 2. Okay. And then for the y coordinate, we get, I totally forgot what's the second one is 1. What's the 7? And divide by 2. Okay. So we end up getting, what does that look like? 6 and 4. That look like it's at 6 and 4. Who knows? So, but close enough. So the coordinates of this point are 6 and 4, and now we just have to use the distance formula, right, to compute that. Length, right? So the length of a prime, the line segment that connects those 2 points, is going to be this big square root, right? The square root of something like 6 minus 1 squared plus 4 minus 3 squared. So y'all can do these calculations now, right? Okay. So, and then I think they want a decimal approximation to something like 1 decimal place. So I'll let y'all do that. So that's what goes in one of those blanks, right? Is whatever the decimal approximation of the square root is. This is the square root of 26. So that's a little bit more than 5 point approximate. All right. One other thing people were, let's see if I can remember. Amanda, so this was your question 17?
Yes.
Okay, so that's a pretty straightforward question, except for the numbers in the problem are a little bit hard to work with, okay, because there are fractions. The reason I say it's a straightforward question is it's just finding the center and radius of a circle, and you have the equation for the circle. So right here, right? So that means you're going to have to use completing the square in order to write that in factored form, right? So you can read off the coordinates of the center of that circle and the coordinates of the, and the value of the radius of that circle. But completing the square on this expression, on this equation, is a little bit difficult because of the 1/4 x and the 1/4 y. Okay, so it makes the arithmetic a little bit messy. So let's look at that also. So y'all remind me of that when I switch back over here to the notes. So let's see, what was that equation? This was problem 6, right? I don't know what problem this is. What is it? 17 or something? 17? Okay. So we have x squared plus y squared, and then something with 1/4 in it. What? Is it minus? Yeah, okay, minus 1/4 x plus 1/4 y, plus 1/4 y, and then where's the 1/32 on the other side? Is it just 1/32? Equal 1/32. So that's it. Okay. All right. So remember now, in the process of completing the square is still the same, even though these coefficients are fractions. So remember, you're going to group the x's together. So put those terms together, and I'm going to leave myself a little bit of room inside the parentheses because remember, I'm going to factor here ultimately. And let's put the y terms together. So we have y squared plus 1/4 y, right? And then leave myself a little bit of room inside the parentheses equal to 1/32. So the question is, what do I add into both of these parentheses so that I can factor these parentheses as perfect squares, correct? And there's a formula for that. You don't have to guess at it. Formula really helps in this case because these are fractions. So remember, you're going to take your coefficient of the x, which is a fraction here, and then you're going to divide that by 2, and then you're going to square it, okay? So let's see now, what is minus 1/4 divided by 2? So is that going to cause what now? 1/8. Yeah, you're right. Okay. So that just gives you minus 1/8, right? Dividing by 2 is the same as multiplying by 1/2. So if you take minus 1/4 and multiply it by 1/2, that's the same as dividing by 2. That gives you minus 1/8, right? Okay. Because when you multiply fractions, remember you multiply numerators and multiply denominators squared, and that turns out to be positive 1/64. So what's going to go in here is 1/64. Okay. So you can just put it right in there, and looks like sort of the same thing's going to happen here, right? Okay. Instead of getting positive 1/4 though divided by 2, which will be positive 1/8. Sorry, instead of getting negative 1/4 divided by 2, we have positive 1/4 divided by 2. But positive 1/4 divided by 2 is still positive 1/8 squared is still 1/64. So we'll just insert in here 1/64. Right now we've changed the equation, right? So how do we keep the equation balanced? That's right, you add it to the other side, right? So you have to add in 1/64 twice also on the other side. Now this looks terrible. We have to factor these two sets of parentheses, but the factoring is easy because this is going to factor as x, and then whatever number you squared here to get the positive 1/64, that was minus 1/8. So you just put x minus 1/8 squared. Just that easy. So you don't really have to think about the factorization. It's all automatic at this point. And for the second set of parentheses, remember we squared positive 1/8 right there. We squared positive 1/8, so you put in a positive 1/8 squared equals 2. But now we do have to figure out what's 1/32 plus 1/64 plus 1/64. Well, let's convert those to 64ths. 1/32 is 2 over 64, correct? Plus 1 over 64 plus 1 over 64. And that turns out to be 4 over 64. And 4 divides into 64, fortunately, 16 times. So you can reduce 4 over 64 to 1/16. So you just get 1/16 on the right-hand side. So there it is. X minus 1/8 squared plus y plus 1/8 squared equal to 1/16. So what's our center? For this circle, this is a tiny little circle. Where is it centered at? 1/8 and minus 1/8, right? Okay. Remember, it's x minus h, y minus k. So the h here is 1/8. But since it's y minus k and you have plus 1/8 here, I have to write the y-coordinate center as -8. And then what's the radius? Well, that's just the square root of the right-hand side. It's the square root of 1/16, but 1/16 is a perfect square. Its square root is 1/4. 1/4 times 1/4 is 1/16. So they have this little tiny radius of 1. Okay. So it all works exactly the same. You just have to be patient with the fractions and don't let them intimidate you. Okay. So don't get intimidated by working with fractions, and don't immediately convert them to decimals. Okay. So try to force yourself to work with fractions. Don't let them scare you. Don't immediately convert them to decimals, because in WebAssign especially, that may hurt you. WebAssign may want exact answers instead of decimals. Okay. Other questions on this one? The only other thing that people were having trouble with was using the, which one? The moon? Oh, well, I have another harder problem, but it's not the moon, coming up in the ellipses. All right, let's see what it says here. Now, remember, you had not learned about ellipses at this point, so you really don't have to use ellipses. That orbit looks like an ellipse. Something is orbiting around the moon, a satellite, and indeed, that orbit will be elliptical. Okay, so we talked about that, right? When objects are orbiting other objects in our universe, the orbits are elliptical. Okay, so we have an elliptical orbit here, and there's the equation for it. All right, and that is the equation for ellipse, but that ellipse does not have center at 0, 0. Okay, that ellipse has been translated a little bit, so you don't have just x squared over 25, you have x minus 3 squared over 25. Okay, but anyway, let's see how we can use that equation, even if we don't understand that that's the equation for an ellipse at this point. How can we use the equation? So it says, from the graph, determine the closest and furthest that the satellite gets to the center of the moon. Now, the center of the moon there is at the origin, right? That's the way they've got the picture drawn. Okay, so center of the moon is at the origin. Notice that the moon is going to be one of the focal points of this ellipse. So they've drawn this picture so that the focus of the left focus of this ellipse is at 0, 0. Okay. All right. So we want to figure out, I guess, what these two points are, right? Okay, here and here. And by the way, what are those in terms of ellipses? What are those 2 points called? Yeah, those are the vertices of the ellipse. These points are not the vertices of the ellipse up here. Right? These are the vertices of the ellipse, right? So want to kind of determine the vertices of the ellipse. But again, remember, at this point, we don't know anything about ellipses. But what we do understand is, oh, the way this picture is drawn, those vertices of the ellipse happen to be what for this graph? Just by, well, it's not really by chance. They've drawn the picture this way on purpose, but what do those vertices of the ellipse happen to be? For this curve, these are called what? Yeah, it's too easy. That's why it seems hard. Okay, I just said for this particular curve, the two vertices correspond to what special points on the curve? X-intercepts, right? Okay, yeah, they've just drawn the picture so that the curve will cross the x-axis at the two vertices, right? Okay, and those are called the x-intercepts. So what we're really asked for here is just find the x-intercepts of this curve. This is just an algebraic question. Okay, all right. So how do we find x-intercepts of any old curve? So let's switch back to the paper there. Did y'all write that curve down? Sort of remember it, but how do you find the x-intercepts of the curve? Do what now? Yeah, at the x-intercepts, y is equal to 0, correct, right? So if you're looking at the equation, what do you do? Was this it? Is that what it was? Yeah. Okay. See, our ellipses, the ellipses that we studied closely would not quite match this equation because our ellipses always have their center at 0, 0, and this ellipse did not have center at 0, 0. So notice you got a little bit more complicated numerator here than we were getting in our elliptical equations. We only had x squared. You didn't have some. Okay. All right. So what y'all just tell me? What do we do to find the x-intercepts of any old curve? Set y to 0, right? Okay. So that's true for any curve, all right, not just ellipses, right? Just in general, if you want to find the y-intercept of some curve in its equation, set y to 0, and then you have to solve the equation for that, right? Okay. So you have a little bit of algebra to do solving the equation, but see, this is just an algebraic problem. It has nothing to do with the shape of the curve, right? This is true. This process applies to any curve. Okay. So let's set y to 0. So when you set y to 0, wow, that really simplifies things, right? Because what happens here? This term disappears, right, completely. So because the y is 0, so you just get x minus 2 squared over 25 is equal to 1. And how do you guys want to solve that equation? That's a proportion equation because I've got a fraction equals, think of 1 as being a fraction, is writing it as 1 over 1, right? And that means you can cross multiply here. So we get x minus 3 squared is equal to 25. And if x minus 3 squared is 25, then I think x minus 3 must be what? The square root of 25, right? So if you square x minus 3 and get 25, then x minus 3 has to be the square root of 25. But don't forget, 25 has 2 square roots, so you have to write them both down. So be careful about that, okay? So x minus 3 is plus or minus the square root of 25, which of course is 5. So you end up with 2 solutions here. I'm going to bring the minus 3 back to the right-hand side. So I get 3 plus or minus 5, which would be what? 8 and negative 2. So these 2 points in the picture, this is 8. Is that what it looks like? Yeah. Okay. All right. So it's 8, and this point is exactly what it looks like there, negative 2. Okay. All right. So what's the answer to the question? What's the furthest it is away? 8 something, and then on this side, the closest it is 2, I guess, right? Yeah. And don't say negative 2 because this is a distance, so you won't have negative. Yeah. Now, this is a similar situation. Okay, it's very similar to finding the intercepts. Here they're saying there are 2 points on the orbit that have y coordinate 2. Oh, they've sort of drawn them for us there, right? Okay, so there's y equals 2. So if you go across to the curve, there are 2 points there that have y coordinate 2, and then they want to know, well, what are the x coordinates of those points, right? What are both of those points, right? So what do we do there? Yeah, okay. Instead of setting y to 0, right, we would set y to 2. Okay. So see, that's very similar to finding the x-intercepts. Finding the x-intercepts would be there are 2 points on the curve where the y coordinate is 0. Okay, where the y coordinate is 0 is the x-intercept. Well, here they're asking there are 2 points on the curve where the y-coordinate is 2 rather than 0. Those points don't have a special name, but we're going to find them the same way, right? Just set the y-equation 2, and then you have some algebra that you have to do. Is that algebra hard? Let's try that. So if I do that, if I set the y-coordinate to 2, what happens here? You get, this term is the same, right? But you get 2 squared over 16 is equal to 1. So we have x minus 3 squared over 5 plus 4 over 16 is equal to 1. And now we have to solve this equation. So this is a little bit harder to solve, but not too much. X minus 3 squared over 25 plus, this is 1/4, is equal to 1. So subtract 1/4 from both sides. So you get x minus 3 squared over 25 equal to 1 minus 1/4, which is 3/4. But now you can cross multiply again, okay, if you want to. So we get 4 times x minus 3 squared is equal to 75. See, I took 4 times x minus 3 squared, this numerator times this denominator, and then 3 times 25, right? And now divide both sides by 4. So you get x minus 3 squared is 75 over 4. And now how do you proceed there? What did we do before at this point? I know this squared is equal to 75 over 4. So how do I get rid of the square root? I mean, the square. Yeah, take the square root of both sides, right? That's what we did before. So you get x, you get x minus 3 is equal to plus or minus the square root of 75, which means that x is 3 plus or minus the square root of 75. Oops. That's the square root of the whole thing. So let me extend my square root. That really is the two answers. 3 plus the square root of 75 over 4. And then the other one is 3 minus the square root of 75 over 4. Did they want this exact or in decimal? That's here.
They wanted it not at 75.
So I don't think they want this in decimals yet. Okay. So so let's write this out. So you could put these answers in: 3 plus square root of 75 over 4, 3 minus the square root of 75 over 4. But let's simplify these a little bit, okay, by hand. So you can't completely simplify them because 75 over 4 is not a perfect square. So this is not going to completely simplify. But let me show you what you can do by hand. So since you have the square root of the fraction, you can break the square root into top and bottom. And that helps because 4 is a perfect square. So its square root is 2, right? So you get 3 plus or minus the square root of 75 over 2. That's better, right? Now, 75 is not a perfect square. So if you want to simplify that, you're going to have to factor the 75 a little bit. So you're going to have to write it as a product. And you want it, hopefully, if you can, write it as a product of a perfect square times some number. Does that work for 75? Yeah, it's 25 and 3, right? So you can write this as 3 plus or minus the square root of 25 times 3 over 2. And now you can extract the square root of 25. That was the point of writing the 75 as 25 times 3. You can extract the square root of 25. It's 5. So you get 3 plus or minus 5 times the square root of 3 over 2. That's it. That's the best you can do by hand. From here out, you're going to have to use a calculator to get a decimal approximation. Okay, so your two possible x coordinates are 3 plus 5 times the square root of 3 over 2. Knows what that number is, and then 3 minus 5 times the square root of 3 over 2. Now, one thing about WebAssign is, and you have to be careful about this. If WebAssign does not ask for decimal point, it probably wants the exact answer. Decimals are not the exact answer. They are approximations to the exact answer. This is the exact answer. Okay, well, the two exact answers. 3 plus 5 times the square root of 2, 3 minus 5 times the square root of 2. Okay. So remember, decimal point does not mean exact, right? Okay. This is exact. Decimal point is going to be an approximation, right? In most cases. Okay. Hopefully that's it. The moon problem. All right. Well, I have another problem. So let's see if we can find it here without. It's on the ellipse homework. So let me open that one. It's another orbit problem. Okay, have y'all looked at that one yet? Okay, so it kind of like the moon problem, actually. Okay, except now you know more about ellipses, right? So let's see, the planets move around the sun in elliptical orbits, and the sun is at one focus. So the point in the orbit, the planet is closest, that is called perihelion. So here's perihelion, right? That's when a planet such as the Earth is closest to the sun, and then furthest from the sun is aphelion. Right? Okay. So in this picture, aphelion. All right. So here we're told some particular planet, unnamed planet here. Okay. Its distance from the sun is 46 million kilometers at perihelion when it's close, and then 70 million kilometers at aphelion when it's further apart. This is going to be highly exaggerated because for most planets, their elliptical orbits are pretty circular. So their perihelion and aphelion are not that different. All right, this is a pretty big difference here. Okay, so we want to find the equation for this planet's orbit, right? Just given that information, right? And what makes this tricky is that the numbers are really large. Okay? So conceptually, the problem is not that hard, but the numbers are big. So that makes the problem difficult. Let's see, I've got a picture of this one. So let me show it to you so I can get you started. See if I scroll down here. I think it's down here somewhere. There it is. Okay. So that's this exact situation, right? Yeah. Okay. This perihelion distance is 46 million kilometers, and this aphelion distance is 70 million kilometers. And we want to find the equation for this orbit, assuming that this is 0, 0. So we've got the center of the ellipse, which is not the sun, right? The sun is at the focus of the ellipse. We've got the center of the ellipse, though, positioned at 0, 0 on a rectangular coordinate system. So we've superimposed a rectangular coordinate system here on this picture, and got the center of that ellipse right there at 0, 0. So we're going to write down an equation that looks like this, right? Because that's what equations for ellipses whose center is at 0, 0. That's what equations for those types of ellipses look like, right? That's what we learned about last time. And we just have to fill in the A and the B values correct, right? And the A value here is going to be the larger value because this ellipse is elongated along the x-axis, right? So we know A is the larger value and B will be the smaller value up here and down here, right? These y-intercepts in this picture. And then the sun is at the focus, and that, of course, we can find the location of the focus, right, by using our elliptic equation, right, that looks like Pythagorean theorem. All right, so see, what do I have to? What do I know? I think I can figure out what A is, right, from the information that's given to me. Can't we figure out what A is? Because if you add the 76 million and the 46 million, right? If you add this distance and this distance, that would give you this total distance from the left x-intercept to the right x-intercept, right? Where we've got the planet located, right? If you add the 70 and the 46. So that would give you the total distance between the x-intercepts. And half of that total distance would be this length, correct? Right? So, so I can find the length from the center out to, where the planet is located, right, at this x-intercept, just by finding half of this total distance. So let's just do that, right? So I think that's going to be the A value, isn't it? So take the 76 million and the 46, no, it's 70, right? So take the 70 million, add on the 46 million, and divide that by 2, and that will give you A, right? So that turns out to be, what happens when you add those together? Get 116 million divided by 2 is 58 million. So you get this really huge number, and you get this really huge number here, and that is what is going to go into this. That's what's going to go into this denominator squared, remember? So you have to take the 58 million and you have to square it. That gives you a huge value. And so in your answer, I think they're going to put the value in scientific notation. So let me open calculator here, and let's try doing this. So we have 58 million, right? Okay, let's square that, and here's what we get. Okay, so that's really kind of hard to read, and he even knows how to read that number, and it's hard to type in because of all of the zeros. So the book is going to enter that in scientific notation, right? Okay, because yeah, the 58 million squared, right, is going to be much larger. Is that what you're asking? Yeah, okay. Yeah, when you square 58 million, you get a really big number, right? Well, you get that big number if the calculator is correct. But the WebAssign is going to enter that in scientific notation because there's so many digits here. Okay, so in dealing with these really large and really small numbers in science, right, we often convert them to scientific notation to make them easier to work with. So let's convert this to scientific notation. And remember, the way you do that is by moving the decimal point, correct? So I'm going to move the decimal point here. I have to move it to the left because I need to get a number between 1 and 10. So let's move it here. Did I kill my calculator? So how many digits do I have to move that decimal point, which is right there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you get this number in scientific notation would be, darn it, in scientific notation, this number would be 3, what was that? 3.364. And the book gives no instructions, but I think they use like 4 decimal places in the problem. So just a heads up there. Times 10 to the 15th power, because we the decimal place. 15 digits. Okay. So that is, yeah, the zero is kind of superfluous. What now? I think in WebAssign, it's going to want times 10 and then exponent of 15. Okay. Oh, and they want between 1 and 10. Yeah, 4 decimal points is what I saw the answer. So that's why I put this extra 0 here. Okay. Now, well, so that's the value that's going to go here in the equation. So see, that's going to be a tough equation to create in WebAssign, because you're going to have to type in fraction, this exponent. You don't need this square, right? Because we've already squared the a value. That's already incorporated into the scientific notation. But you got to type in that times 10 and then that exponent in that denominator. How do we find the other values here? What is C? C is going to be this distance, correct? The distance from the center to the focus. The sun is the focus. So let's see, you know this from the center to this X-intercept is 58 million, but this distance was 46 million, correct? So that means this distance must be 12 million? I think so. Because added up, the 46 million and the 12 million have to add up to 8 million. So you know what the C value is now, it's 12 million. You know what the A value is, that's 58 million. So you can plug those into this equation and solve for B. Right? So there's how you find the B, and then, or actually the B squared, that's what you're really interested in. And that's what you plug into. Finish off the equation for the, okay. I'll barely see that. That's 12 million. C. Okay, so just a heads up on that problem at the end of that's the last problem in the ellipse homework. Okay, well, I haven't been talking to people on Zoom. Okay, so I hope everyone is there watching what we're doing. I'm going to talk to you now though. Okay. All right, so let's go back here, and I've got a little recall practice for you. So instead of me doing all the work here, let's let y'all do a little bit of work with straight lines. Okay, so let's try these 2 problems first, and then we have one more. All right, so everyone at home, right? Let's try these 2 problems. Okay, right? Just see if you can fill in the blanks here about the facts about parallel and perpendicular lines. So the slopes of parallel lines are what? Okay, how could we complete that sentence? And then in the most efficient way, how could we complete that sentence? And then part B there, the slopes of perpendicular lines are, notice I've left 2 blanks. May have to say that with a little bit more. Most efficient way of saying that is 2 blanks, but if you have to use a little bit more words to describe the relationship of slopes of perpendicular lines, and that's fine also. Okay, so what about the slopes of parallel lines? What about the slopes of perpendicular lines? Can you fill in those blanks? Can y'all do that at home for me now? Okay, so fill in those 2 blanks. Just take a minute and see if you can remember what to put there, or if you find it in your notes in a short period of time. What problem number, Fernando, at home, are you asking me this question? What problem number is this? The one I'm looking at? Okay.
No, I was looking at the wrong homework assignment. I found the question.
All right, well, the problem we're looking at now is just what you're seeing there on the screen. Okay. Oh, well, all right. So Kenneth there, Kenneth Liu, right? Answered for chatted it in, right? So guys here in the classroom, and it says that slopes of parallel lines are the same. Yeah, that's right. Okay. So parallel lines have the same slope, all right? Or you can put equal or anything that's synonymous with the same or right would fit in there. Okay. And Kenneth, your answer for B is really good also. All right. The slopes of perpendicular lines, they are reciprocals of one another. And you said opposite. And I understand what you mean there. A better way of saying that would be negative. Okay. Opposite has other meanings. Okay. But more precise here is we want them as negative reciprocals of one another, right? So if you have a line and you know a line is perpendicular to it, just take the line of the slope of the first line, right? Flip it, so form the reciprocal, and then change the sign, right? Okay, that's how you get the slope of the perpendicular line. Okay, excellent. All right, did y'all recall that? We're gonna look at that again later today because we're gonna actually demonstrate these things as I promised last time. What about now? Let's look at just a little applied linear equation. All right, so this is a linear equation for sure, right? Because it fits the form of a linear equation, right? And remember, I told you, you can usually recognize linear equations easily because the unknowns, the variables, are just raised to the first power. So this is y to the first power, x to the first power. So that is indeed the equation for a line, okay? But this one is definitely even more obviously the equation for a line because this is written in slope-intercept form, right? Okay, it's written in slope-intercept form because it has been solved for y. And that being the case, we can read off the slope and the y-intercept, and that's what we're going to do in this problem. So this tells us what the size y here is the size of an experimental mice population is modeled by this linear equation. And X here is elapsed time again. It's the number of months after the experiment begins. All right. So the two questions there is what's the initial population? So how many mice did we start with? And then what is the slope of this line? And what does that mean in the context of the problem? What is that telling us about our mice population, right? What's the slope mean to us in the context of this problem? Okay, so see if you can write down that initial population, and then can you find out what the slope is, and then after you found the slope, can you explain what is that telling us about the mice? Okay, so what's the practical implications of whatever value you get for the slope?
The initial value is 50, right?
Practice, so you don't have to just want to remember as best you can from last time. What, Ahmad? Do you have a question, or were you?
Oh, I was answering A, but
Okay, well, wait a minute there, then I'll call on you. All right, Ahmad. All right, so
I might disconnect this. Give me a minute.
uh-oh. Okay, so all right, guys, so what is the initial population? 50, right? Okay, so yeah, so the initial population is 50, and that really corresponds to the y-intercept here, right? The y-intercept for this line is 50, right? Because this is in slope-intercept form, so this constant is going to be the y-intercept. So the initial population is 50. So we started with 50 mice, and what's the slope here then? Also easy to read. Yeah, Amanda. Be careful now. No, it's a number, so the x wouldn't be included, but -2, right? Yeah, okay. So, and the sign is really important there with slope, all right? Because that sign will tell us if our y values are increasing or decreasing as x goes up, okay? So usually we're thinking of x going up, but y may go up or down as x goes up. In this case, the y value is going to go down, right? Because the slope is negative. So in fact, how do we describe that decrease in y? So what's our interpretation of slope here? What now? Right. So what's decreasing 2 mice per month? What? Yeah, that's right. Okay. So our y, which is the mouse population, right? So the population it's changing, correct? But since our slope is negative, that change is a decrease, right? So the population is decreasing, or you could say falling, right? Okay. And then the slope tells us how fast that decrease is occurring, right? So the population is decreasing by 2. Don't put -2 because you already included the negative information, the fact that the slope is decreasing, right? So population is decreasing by 2, and then 2 what? Well, that's a population of mice, right? So it's by 2 mice. Each time x increases by 1. So every month that goes by, how would you say that more? Or normally? Per month, right? Okay. So the mouse population, the population is decreasing by 2 mice. That per month is really important. Okay, so that phrase has to be in there. Get the slope information correct. Okay, can't say just the population is decreasing by 2 mice. Okay, that's happening every. Now you don't have to say per month. You could say this in each month, or each month that passes, or every month that goes by, or something like that. But that idea that this decrease is happening each month is important, so it has to be interpretation. Okay, now let's look at the hardest problem, though, but it's not a hard problem. All right, so last bit of recall practice here. So in that previous recall practice, I gave you the equation, and we were talking about the equation, right? Here, I'm going to give you the picture of the line, the graph of the line. So there's a line, a little bit wavery, but imagine that's a line. Okay, it's supposed to be a line connecting those 2 points, -4 and 6, and 5 and 1. Okay, so what I want to know is what's the equation for this line. So we're just working backwards, right? Got the picture and just want to write down the equation rather than starting with the equation. Start with the graph and write down the equation that corresponds to that particular picture. So this is really important process with all types of curves, being able to look at a graph and write down the equation for that graph, but it's particularly important for lines, all right, because this is the simplest type of curve. So if you can't do it for lines, then you're not going to be able to do it for more complicated types of curves as well, right? So you got to really get this right for lines, and this is something that's frequently missed on tests, all right, but it's easy. Okay, it's a very easy process. All right. So where do we start when we're writing down equations of lines from some sort of graphical description? Either could be, you don't have to have a picture drawn. You could say, oh, I have a line and it goes through these 2 points. What's the equation for the line? Okay, but here we do have the picture. All right. So what's the first thing that we want? The slope, right? Yeah, you're going to start with the slope. When you're writing down equations for lines, you need the slope, okay? So almost all the time, you're going to first try to figure out what's the slope, okay? But do we know what the slope is here? Can we calculate that? Do we have enough information to figure that out? Yeah, because all we need is 2 points, right? So if you've got 2 points, you can calculate the slope. There are other ways to find slope as well, all right, sometimes, from information that's given to you, but here we've got 2 points, so that makes it very easy for us to calculate the slope. All right, so I'll do that for me here. Calculate slope of this line. See if you can remember how to do that. You've done that in multiple classes, so and we just reviewed it last time, so I'm sure you can write down. Sure you can recall now. Writing down the slope for that line. So you guys at home be doing this, right? Okay. Now this is -4. Yeah, that's a 4. -4, 6, and 5, 1. I think I have those points plotted properly. And I was doing that fast, so. Yeah. -4 and 6 and 5 and 1. Okay, so someone on Zoom, did y'all, someone on Zoom, did you calculate for me the slope? Did I give you all enough time? Someone out there in Zoom land. You can just tell me, or you can chat it in. Ishan? Are you gonna tell me?
Sorry, one second. I got my equation messed up.
Okay, all right. Someone else out there can beat Ishan to it. Just what do I put in here to calculate the slope? You guys are shy, so I'm gonna have to call on you. Y'all don't tell me. Mohammed? Star Wars?
Yeah.
What did you get?
-5/9.
-5/9? Okay.
Yeah.
So let's see. You took 1 minus 6. Is that what you put in the top?
I had 1 minus 6, and then 5
Over what?
plus 4. Well, over 5. Technically, 5 plus 4.
Yeah. 5 minus a -4, right? Which is 5 plus 4. Yeah. Okay. So that's perfect, Mohammed. So you took the difference in the, oh, did we do that right? Uh-oh. Did I write it down wrong? Mohammed, did I write it down wrong?
I think that's right.
I think I got it backwards, didn't we? Because when you're, Mohammed, when we're calculating the slope, remember, it's the difference in the y coordinates on top. Okay. And the difference in the x coordinates goes on bottom. Is that what you put, Mohammed?
Is that what?
Yeah, I think it's going to be. Oh no, that's what you did put. Right. Sorry, I'm reading it backwards. That's why I'm confusing you, Mohammed. That's why you were hesitant to answer me there. Okay, so 1 minus 6 over 5 minus a -4. Perfect. All right, which is what? -5/9? Okay, yeah. So there's our slope, -5/9. Okay, that's negative. So the y values are decreasing. Indeed, as we go from left to right, right, as x is going up, the y values are decreasing. Okay, that's why the line is going down. And again, that -5/9 tells us how fast those y values are decreasing as our x values increase, correct? Okay. Now, let's see if we can write down the equation. This is the easy part, because once you've got the slope, that's really the key thing in writing down the equation for the line. All you have to do is use point slope form, all right, to write down the equation. And remember that point slope form is y equals to the slope times x minus x coordinate of some point on the line, any point on the line, and then plus the y coordinate of that same random point off of the line. So we already calculated the slope as minus 5/9. So now we can use either one of these 2 points in writing down the point slope form. So let me use the second point there. So we have x minus 5/9 times x minus 5 plus that y coordinate of 1. That's it. It's just that easy. There's the equation for that line. And unless you're asked to simplify it, okay, you don't have to simplify, just write it down. All right, so there it is written down. Sometimes you will see the point slope form expressed this way. You take y minus the y coordinate of the point that you're going to use equal to the slope times x minus the x coordinate of the point you're going to use. So sometimes that 1, you'll see it written the left-hand side. That's still the same equation. Okay, so that's still an equation for the line, right? So easy once you've got the slope to write down the equation. So when that comes up on the test, that should be an easy problem, right? If you calculate the slope, just remember the point slope form, and you can write down the equation for the line. Really simple. Okay. All right. So we're done with our recall practice. So let's stop. Ben, do you have a question? No. Any point will work. Okay. Any point will work. Actually, I think we derived that point slope form last time. We showed why that equation is the equation for the line, and we just picked a random point off of it. So yeah, any point on the line will work. The reason that is true, basically, is the fundamental feature of straight lines. For straight lines, the slope between any 2 points always comes out the same. Calculate the slope points always the same. All right. Okay. So and that's really what makes lines lines. Other curves do not have that property. Okay. All right. Let's stop there and let's take a few minutes. So we'll come back at 11:25, and then I have to show you then what we were talking about earlier, why it's true. So why do parallel lines have the same slope? Why do perpendicular lines have this their relationship of being negative reciprocals of one another? Why is that true? So we're going to look at that when we come back. All right. Okay, so we're going to look now at why these relationships between the slopes of parallel and perpendicular lines are true. These are easy things for us now to, well, when I say easy, okay, we have all the tools that we need to understand why these things are true. So we want to, we're going to prove these things, why parallel lines have the same slope and why perpendicular lines, why their slopes are negative reciprocals of one another. So we can exploit some of this knowledge that we've developed. All right. So let's start with the easier, what appears to be the easier fact, or the more obvious fact. Okay. And this is called the parallel line theorem. All right. And it says exactly what you expect. It says non-vertical lines. Notice that there's this caveat there that the lines have to be non-vertical, right? Non-vertical lines have the same slope if and only if they are parallel. I want to point out that phrase, if and only if. That's important in logic, and explain what that means. Okay. In logic, if you say if and only if you use that phrase, you mean that the implication is true in both directions. So what that means is that if you have lines that have the same slope, they must be parallel. Right. So if you know 2 lines have the same slope, then you know those lines have to be parallel to one another. But the opposite is true as well. If two lines are parallel, then they have the same slope. So the implication is true in both directions. So this is a very powerful relationship between the slopes of parallel lines, right? Okay. If they're parallel, they have the same slope. Or if they have the same slope, if you know two lines have the same slope, then you also know that they are parallel. Let's start with the easy direction first, because this is kind of going to be very kind of obvious to you now. All right, so let's start with this statement. If lines are parallel, so if we know two lines are parallel, someone tells you if lines are parallel to each other, then why can we deduce immediately that they have the same slope? So when we calculate their slopes, why do we know they're going to turn out to be the same? All right, so I've just drawn a picture here of this situation. Very general, the picture of this situation. Suppose we have these two lines. I called them L sub 1 and L sub 2, and suppose I know that those two lines are parallel to one another. So that's a given. So I know, okay, these two lines are perfectly parallel. That means they're the same distance from each other at every point, right? Okay, all the way to the right and all the way to the left. All right, so how do I know then that they have the same slope? Well, what you do here is just in this picture, just calculate their slopes, okay, right? Okay, and see if they come out to be the same. Now you might think, how am I going to know if they come out to be the same? Because this is a very general picture, right? It's very abstract. I've just got this abstract line L1. I know these 2 points on it, but I haven't specified the exact coordinates of these 2 points, right? And then I've got this second point L2. I know it's parallel to L1, but again, I've just put these 2 abstract points here on this line, but I haven't really specified the coordinates of these points. These can be any 2 points on the line L2, and these can be any 2 points on the line L1. Well, we'll get to that, okay? All right, so let's go ahead and calculate the slopes of these 2 lines, all right? Not much calculating to do, right? To calculate the slope of this top line, which I'm calling L1, let's call that slope M1. Well, you always do it the same way, right? You're going to calculate the rise, right? And you're going to divide that by the run, right? Okay. And well, what is the calculation for the rise? Well, you take the difference in the y coordinates, right? See, right, Mohammed? That's what I was confusing you with a moment ago. So you take the difference in the y coordinates, right? Y4 minus y3 in this picture. They're the 2 y coordinates, right? And you divide it by the difference in the x coordinates, right? X4 minus x3. There's the rise and there's the run, right? So, okay, cool, right? So that's the slope, and that's all I can say about it because I don't know the exact values for any of these variables, right? What about for the second line? Well, let's call its slope m sub 2, since I'm calling this line 2. And let's calculate its slope. Well, it's going to be rise over run again, right? Just like always. So the rise here would be y2 minus y1, right? Over x2 minus x1, right? And what I'm trying to figure out is, why do I know that these 2 calculations are always, did everyone sign? Okay. So why do I know that these 2 fractions, these 2 calculations, why do I know they're going to come out to be the same? Well, because, right, we know these lines are parallel to each other. Then what about these 2 triangles? Similar, right? They're similar triangles, right? Since these lines are parallel, these 2 triangles have to be similar to each other. That means then the similar triangle theorem applies, right? So remember, when you take the ratios of corresponding sides in similar triangles, you get equal fractions, right? So if you take this ratio, this side, and divide it by this one, this vertical side divided by this horizontal side in the top triangle, that gives you this quantity, right? That's got to be the same as if you take the vertical side here and the horizontal side here and divide them. So if you take this and divide by this, that will be the same as this vertical side divided by this vertical side in the top triangle, because these are similar triangles. So these 2 fractions really are the same, right? Okay, these 2 slopes really are the same. Okay, that's just a direct consequence of the similar triangle theorem. That's really all you have to say. Okay, by the similar triangle theorem, which we already were taking to be true, right? By the similar triangle theorem. These calculations, the ratios of these sides are same. So those ratios are the same, or in other words, M1 equals M2. The slopes are the same. So easy, but just similar triangles. Now, the other way is a little bit more, the other direction is a little bit more fun. So see what here I showed was if the lines are parallel, then they have the same slope. But the other way is true also. If you have two lines and you know they have the same slope, then they have to be parallel. That's a little bit trickier to think about. All right, so let's draw a picture here. And I've drawn two lines, just like in the prior picture, and they sure look like they're parallel, okay? But I cannot make that assumption yet, all right? What I am going to assume, though, is they have the same slope, right? So this line and this line, I'm going to assume, the top and the bottom line, I'm going to assume they have the same slope. What I'm going to demonstrate is that they're parallel to each other, okay? All right, so all I know is have the same slope. All right, so here's what I'm going to do. I'm going to, on one line, I'm going to draw a vertical line up, okay, until I hit the second line, okay? So I'm going to call, so I'm just going to draw a vertical line up from the bottom line to the top line. I'm going to call that distance V1, all right? I don't know what that distance is, okay, but we're going to call it. Now, from the top line, I'm going to draw a horizontal line across. So this is a horizontal line across until I come back to the bottom line, all right? So you see what I did there? I started at the bottom line. I drew a vertical line up till I hit the top line. And then I'm going to draw horizontally across until I come back to the line I started with, all right, which is the bottom line. And then from this line, I'm going to draw vertically up again until I hit top line. So I end up with two vertical lines here that are connecting the top and the bottom line, right? V1 and V2. And then I have this horizontal line across between the two lines. So this line goes vertically, connects the two lines. This line goes vertically, connects the two lines. Then I have this horizontal line also that connects the two lines. Now, the reason I drew this particular picture is notice that I end up with two triangles here, right? You've got this triangle. So you have this bottom triangle, and then you have this top triangle. Now, the reason I like having those two triangles is, so this bottom triangle and this top triangle. The reason I like, oh, also I have a parallelogram too, right? But that's not important. All right. Well, I don't know if it's a parallelogram yet, because I don't know if these two lines are parallel yet. So let me back up. I said too much. All we know is those two lines have the same slope, but I'm not sure they're parallel yet. Now, how do I calculate the slope of this line L2? From this triangle, how do I calculate the slope of the bottom line, which I'm going to call M2, by because it corresponds to L2. So yeah, how do you calculate the slope of this line from this picture? Well, don't we have a rise and a run, don't we? Right? See, if you think of these two, connecting these 2 points, what's the, see, those 2 points are on the bottom line, right? Okay, what's the rise between those 2 points? Isn't it this line? What's that length? V1, right? So the rise is V1, and what's the run? If you go from this point to this point, what's the horizontal distance? H, right? So you know the slope of the bottom line is V1 over H. Now you don't know what V1 is, okay? So you don't have a number there, and you don't know what H is, but in the you don't know the numerical value for H, but in the picture, you know that the slope of the bottom line has to be 1 over H. Now, what about the slope of the top line? Now I can do the same thing, right? Because I have this triangle. So if you go from this point to this point on the top line, what's the rise? What? V2, right. The rise is V2. And what's the run? H. Okay, so there you've got the two slopes. And what do you know about the two slopes? So what's our assumption? Look at the top there. They're the same, right? Okay, we don't know that the lines are parallel. I've drawn them so that they're parallel, but that might be a faulty thing, right? But I do know that the lines have the same slope. So these two values are the same. So let's write them down. V1 over H is equal to V2 over H because the slopes have to be the same. So guess what? You can cancel from that equation. What do you have on both sides here? Yeah, you can cancel the H's. And you just end up with what? This distance is the same as this distance. Oh, guess what? Okay. If the vertical distance between two lines is always the same, what do you know about those two lines? They're parallel to each other, right? Okay. They have to be parallel, right? Okay. This distance are the same, then those two lines have to be. And remember, I just picked any 2 points, right? So the vertical distances between the two lines always the same. Such lines have to be parallel. Yeah, Jen. No, we didn't. We never assumed that they were equal. We just ended up with that here. Okay, but we assumed that the slopes were equal. Yeah, that's the assumption. So we get to assume that because that's what we started with, right? So we assumed that the slopes were the same. So we ended up with these distances are the same. If those distances are the same, though, the lines have to be parallel to each other, right? Okay, so it's true in the other direction. If you have two lines that have the same slope, you know they are parallel. This also is only true for non-vertical lines. Vertical lines, you can't have vertical lines. Of course, these V1 and V2 are vertical lines. This theorem does not apply to vertical lines. Okay, and the reason is vertical lines do not have a slope measurement. Okay, all right. Cannot calculate the slope of vertical lines. So none of this applies because there's no slope for vertical lines. All right, that was kind of the easy one. Now we're going to get to the hard one. All right, so that's the relationship between perpendicular lines. So y'all are going to have to help me with this one because this one requires some work. All right, so suppose we have lines that aren't vertical and also not horizontal. So I'm also going to assume they're not horizontal, and but they're perpendicular. So that's true if and only if their slopes are negative reciprocals. We're only going to bother with proving one direction here. We're going to show that if the lines are perpendicular, their slopes will be negative reciprocal. So I'm not going to try to do the other direction. If the slopes are negative reciprocals, then the lines are perpendicular. Okay, we're only going to assume that if we have two perpendicular lines, their slopes, we're going to show their slopes are negative reciprocals. All right, so I'm just going to draw two perpendicular lines. Now I'm going to move them though, so I'm going to translate them though, so that their intersection point is at the 0, 0. So so if wherever the perpendicular lines are drawn, I'm going to think of just picking them up and moving that picture so that their intersection points are at 0, 0. That will not affect the slopes of the lines, okay? But it makes my arithmetic here in algebra a little bit easier. So I get a picture that looks like this. So there are two two arbitrary perpendicular lines. Okay, and again, I'm going to assume that they intersect at the origin. So they cross right here at 0, 0. So they're perpendicular, right? So that means the angles between the lines, right, is 90-degree angle, right? So they meet at a 90 degree. So this line I've labeled L1. Its slope is M1. I don't know what that slope is. Looks like it's positive in this picture though, right? Because this line is going uphill from left to right. And then this line, I've labeled that line L2, called it slope M2. I don't know what that slope is, but looks like it's going, looks like it's negative, right? Because this perpendicular line is going down from left to right. All right, now here's where I have to be a little bit artful. I'm going to come back in here and I'm going to draw in a vertical line into the picture. I'm doing that to create some triangles. And, you know, the reason I want some triangles is because I'm going to calculate some slopes. So I'm going to come back in and I'm going to draw in a vertical line, right? But I'm going to put that vertical line right through 1 on the x-axis. So that's really important. I'm going to draw the vertical line so it crosses 1 right on the x-axis. So there's that vertical line you can see drawn into this picture. Of course, that vertical line is going to cross the top line and the bottom line, right? And the place where it crosses the top line, that point, I'm going to call that A. And right here where it crosses the bottom line, I'm going to call that. So when you put in this vertical line, notice you get a bunch of triangles here, right? You get this big triangle. Looks like this. So this big triangle. This is a right triangle because this angle is 90 degrees. So it's hard to tell, but that big triangle that connects the origin B and A, that is a right triangle because you know this angle is 90 degrees because the lines crossed each other at a 90-degree angle, right? So I'm going to label the sides here, just like we would in the Pythagorean theorem. I'm going to call this side A. I'm going to call this side B, and then this long side here that goes, that corresponds to this vertical line, I'm going to call that C. So that's that long side right there. And remember, that line goes through 1 on the x-axis. Now, you have 2 other triangles here. You've got this small triangle on top, and you've got this smaller triangle on bottom. These are also right triangles because this is a vertical line. So this small triangle on the top and the small triangle on the bottom, these are also right triangles. So the Pythagorean theorem also applies. What's the length of this side? 1, right? So that's important to keep in mind. This length is. Now here's what I'm going to try to figure out. Okay, what is this length? And what is this length? So what is this length? And what is this length? Now that total length I gave a name to, right? That total side here, what did I call that? C. But now I'm trying to figure out what's this little piece up at the top and this little piece at the bottom. When they both add together, they have to give me the total value for, C, right? Okay. Here's where the slope idea is helpful to me. What did I say the slope of this, the top line was? What did I call that slope? No, right there. What did I call it? M1, right. I called it M1. Now, how would you, from this picture, how would you calculate the slope of this line? From this picture, how would you calculate the slope of this line? It's going to be what? Rise over what? Run. So here's the rise, right? And the run is what? 1. So you know that M1, the slope of this top line has to be this rise over 1, which means, since you can just drop the 1, what's the rise? What's the rise equal to? Just what? Just, you can just drop the 1 since the denominator is 1 here. So what do you get? Rise is equal to what? M1, yeah. Ah, so this length is M1, right? Whatever the slope of this line is, that's what this length has to be. Now, look, you can use parallel logic. Guess what the length of this line is going to be? It's going to be the same as the slope of the second line. What did I call that? M2, right? Okay. So this length is M2. Same as the slope of the second line. Because if you take M2 over 1, you have to get the slope of this line, right? And that's got to be M2. That's what we said the slope of that line. So what does that mean the coordinates of this point are? Right here, the point B. What's its x coordinate? 1. What's its y coordinate? M2, right, sure. Because this length is M2, right? What is the coordinates of this point A? 1 and M. All right, now we're in business here. Can you calculate for me what is the length A here? All right, so what is this length? So A, that I called A, what is A equal to? All right. So that's the distance from the origin to this point, which you know is what? 1 comma M1. All right, so calculate that length for me. And I also want you to do the same thing for B. It's going to come out almost exactly the same. So what's the length of A? What's the length of B? All right, so what's A and what's B? Just use the distance formula to find the distance from this point to the origin. Find the distance from this point to the origin. All right, so write those down for me. You won't be able to completely simplify what you get, okay, because you're going to get an expression, all right, okay, but just write down what you get. I'm going to look here. I'm going to go around at watch, Bobby. Yeah, use the distance. So, subtracting 0, so get rid of it, right? Okay, everyone see what you put there now? Okay. So, just get whatever. Sure. Square. Once. Yeah, that's it. Same thing.
Because I'm gonna.
Square. So. Remember the distance? Something. Okay, now just remember that. The picture on that. So that's see. See. I know the algebra is making a little bit hesitant. So. No. And then do the same thing. That's. Okay. All right, so that was good. That was very informative. What y'all wrote down. So let's write it down right. So for you guys at home, all right, you probably have the same questions when we're calculating this length A, right? How do we do that? You're just easy to get confused by using variables, okay? But remember, the variables are at some point just numbers. You just treat them like numbers. So this length A, right, from this is 0, 0, the origin to this point, okay, is going to be using the distance formula, right? You take the difference in the two x coordinates, right, and square that. Well, the x coordinate here, as we discovered, was 1, right? The x coordinate at the origin is 0. So you have 1 minus 0 squared, okay? That's all there is to it. Plus, now, the difference in the y coordinates squared. So the y coordinate of this point is m1, as we discussed, right? What's the y coordinate of the origin? 0. So you have m1 minus 0 squared. That's an m sub 1 there. And that's it. Now you can make this look a little bit prettier, but not much, because 1 minus 0 is 1. And when you square that, you get 1. Okay. And then m1 minus 0 is just m1. You square that, you get m1. So you have m1 squared. That's it. Okay. So that's that length A. Can y'all guess what doing the same thing for B is going to give you? Same, except you'll have what? 1 plus what? M2, right? You'll get M2 squared. That's the length B. So you know what this length is. You know what this length is, right? Okay. Now, all right. Remember, A and B, though, are part of a big triangle, this big triangle. So I want you to calculate for me now C using the Pythagorean theorem. What is this distance C using the Pythagorean theorem? You know what this length is? We just wrote it down, right? You know what this length is? So calculate for me C, okay, using the Pythagorean theorem. You know the Pythagorean theorem, right? A squared plus B squared equal C squared. You know A, you know B, so you tell me what C is, okay? All right, guys at home? Same thing, all right? You know A, you know B. Tell me from the Pythagorean theorem what is C, okay? Not gonna be pretty, but just write down what we, okay? Ah. What C? C. C. C squared. Yeah, all of them, all the way across. But Evan, um, values. Just a- So, XC is this. No, A is. Right? C is this long one. What A is? Oops. A. Square root. Yeah. Perfect. You. Perfect. Yeah, y'all doing beautifully. That's what C do. So. I would see it. Okay, yeah, y'all did really good. So I hope you guys at home did good. The class did really good on writing that down. All right, so let's fill into our Pythagorean theorem. Let's fill in A and B so we can solve for C. So we know A is the square root of 1 plus m sub 1 squared. That's at length A in the picture. That's this length A in the picture. And but we're squaring this, right? Because this is the Pythagorean theorem says you take A and square it. That's really convenient here because it's going to cancel this square root, okay? So that's nice. Plus, and then same thing for B, right? It was the square root of 1 plus m sub 2 squared. Square that square root equals to, don't forget it's equal to C squared, however, okay? It's equal to C squared, not just C, but C squared. So get rid of the square roots then, because that squaring gets rid of the square roots. Of course, you can add the 1 and the 1 together, so you get 2 plus m sub 1 squared plus m sub 2 squared equal C squared. But now what's C equal to then? How do you get rid of the square on C? Take square root, right? So you get C is the square root of all of this. So notice you're kind of putting the square root back, but in a slightly different way than we had it before. So there's the length of C. If we can remind ourselves, all the way up in this picture, that was the length of C. That's the distance all the way from this bottom point to this top point is this square root. Okay. Now, however, here's what I claim. Man, we made our work, we did too much work. Okay. To calculate the length of C, we use the Pythagorean theorem, right? With the A and the B. But why do you need the Pythagorean theorem? Because this is a vertical distance. That's a vertical distance, right? That's the vertical distance from this point to this point. So you should be able to calculate that vertical distance really easily, right? It's just going to be what? This distance and this distance added together, right? But what is this distance? Just this distance. What do we say that? What do we have it there? Yeah, it's M2, right? Okay, but we have to be a little bit careful. M2 is a negative number, right? Okay, M2 is a negative number, right? So, M2 is a negative number. This is a negative number, and since you want it to be distance, what do? How do you make a negative number positive? Multiply by -1, right? What's this distance? Can you see it there in the picture? What's this distance? M1, right? So that length of C is really easy. It's just the negative of M2 added to make this positive, right? Plus M1. Okay. Another way of saying that is just take M1 minus M2. That will also give you this distance. Because it's a vertical distance, you just take the difference in the y coordinates. So you can find the vertical distance easily. So wow, we did a whole lot of work here for, seems like we did too much work, right? Because C is also equal to M1, just M1 minus M2. Now, now let's take this equation because we're going to look at this equation. All right. So we calculated the length of C using the Pythagorean theorem, and then we just remembered, oh, that's just a vertical distance. So I could just take the difference in the y coordinates. That would give me also that distance. All right. Now let's start simplifying this equation. So forget about the C for a moment. Both of those things are equal to C. Let's try simplifying this equation. How do you get rid of the square root? Square. So I'm going to square both sides to get rid of the square. Now, this side is easy to square because what happens? Square root just disappears, right? What happens on this side? This is a little bit harder though. So can y'all do this for me? You got to multiply this out. So what happens when you multiply out M1 minus M2? Well, let's see. What's M1 times M1? That's M1 squared. M1 times a minus M2. Well, I don't know what that is. That's just M1 times a minus M2. So it's going to be negative. And then here it is again, right? M2 times M1, but the M2 is negative. So you get that again. I'm going to write the M1 first. And then minus M2 times minus M2 is what? Plus M2 squared, right? Wow, this is quite nice because look, this cancels, right? This cancels and this cancels because you have them on both sides of the equation. So I get just this. 2 is equal to minus 2 times M1 times M2. Let's solve this equation for M1. So how can you solve for M1? What can you divide out here on the right-hand side? Minus 2 and 2. So let's see what happens. We get M1 is equal to the 2's divide out, and look what you end up with. Oh, what does that tell you? They're negative reciprocal, okay? That's exactly, that's right. The slopes are negative reciprocals of one another, just as promised, okay? So there it is. When you have, took a little bit to get to that, right? Okay, but when you have lines that are perpendicular, their slopes, no matter what they are negative reciprocals of another. Okay, you can also solve this equation for M2, and you would get M2 is minus 1 over M1. Okay, slopes are negative reciprocals. Cool. All right. So now you know why this fact is true. Not just that it's true, but now you know why it's true from this picture. Okay. Well, the parallel lines that have the same slope is a lot easier, right? Okay. This one's a lot harder to understand, but that makes sense, right? That's a more complicated relationship. Okay. All right. So, wow, now we know lots of things about straight lines. All right. So, I'm going to start utilizing that knowledge in various ways. Okay. Get to use straight lines all the time in math. All right. So, next time now, we're going to step back and we're going to look at curves like straight lines, but also circles and ellipses from a little bit more abstract viewpoint, like a mathematician would think of them. And the reason that abstraction is useful to us is it gives us some insight into the differences between curves. All right. Obviously, ellipses and straight lines, or circles and ellipses, they're not the same things, right? Okay. And by considering curves in a little bit more basic way, we can understand a little bit better about what really are the key differences between different types of curves. Okay. All right. So we'll take that up next time. All right. So, well, you got homework due tonight. So be sure you finish that. Keep up those good homework scores. right? Okay, that you started with on that first homework. And I'll see y'all on Wednesday.
Professor, will you be putting the recording on Blackboard?
Will I be putting what on Blackboard?
The recording of the class. I had some connection issues.
Yeah, I always put that on Blackboard, so that will be on.
Okay,
Okay.
thank you. See you Wednesday.
All right.